Hello everyone, hope everybody is doing well. In this lesson today we're going to explore some of the limits that algorithms have. We're going to go and look at two main types of limits. So first of all, there are what are known as undecidable problems. All right, and so these are problems for which no algorithm in theory or in principle can be created to solve the problem in all cases. And that the second type of limit on the algorithms are so-called intractable problems. And these are problems for which we have solutions for some, in some cases, but in general, the algorithms are too efficient to solve the problem as the number of inputs grows so large that it becomes unrealistic. All right, so let's start with talking about decidable problems. So a decidable problem, by definition, is one for which an algorithm can be constructed to answer yes or no, or to make a decision for all possible inputs. So for a simple example would be the problem of determining if a number m is even or not. So given any number m, we can write an algorithm that will answer yes or no, that the number is even or not. An undecidable problem, by contrast, is one for which no algorithm can be constructed that will always lead to a correct yes or no answer. And this is a highly theoretical area of computer science research, so we're not going to go too much into details about that, but to kind of let you know a little bit of how this came to be, we have, stemming back from the 1930s, forward here, we have a gentleman by the name of Alan Turing. And Alan Turing is one of the first computer scientists and one of the most famous out of the computer scientists to prove that there are undecidable problems, to prove and focused on a problem that's very easy to state. It's so-called halting problem. So given an arbitrary computer program with an arbitrary input, to decide whether or not it has an infinite loop. Now this problem can be solved for certain programs, but or I say such as for things that we've been writing. But in general, there is no way to solve this problem for any program in any inputs, and that's what Turing proved, and was quite a revolution of the time. Because at the time, it was thought that algorithms could basically solve any problem that a computer scientist could think of and to have identified. And so many undecidable problems, were put forth, and the halting problem, prior to the halting problem, the computer scientists believed that, they can take care of it and they'll find an algorithm to prove it. But with Turing and his, thought experiment, he basically said that, no, that would not be the case. So to kind of maybe put it in a little bit better perspective, and I don't want to go too much into detail of it, but so if we have a computer system, all right, and this is, we'll call it just HALT, or H for short, and this program is going to have two inputs, all right, and so when the inputs come through, there can be one of two options, or one of two end results. Ultimately, will the computer halt, yes or no? Will the computer operate, yes or no? So if the computer continues to operate, so yes, then what we're saying is that we are going to have an endless loop. So the computer is just going to keep looping and looping and looping based off of what the inputs provided into the mechanism or into the algorithm say. If the computer system, though, does not continue to go, well, then what we say is that the output or the end result is to halt. So now if we were to say, what happens now if we take this machine, this algorithm, call it what you will, and it has obviously certain outputs, why don't we feed these outputs back into itself? So rather than feeding different inputs into the halt machine, we're going to feed its own outputs as inputs. All right, so that means that the input, here and here, well, now we're going to have H plus, which is going to regulate the inputs, which were the outputs previously. And we're going to say that we'll have an H plus input that will halt, and we'll have an H plus input that will not halt. All right, and so these inputs now get fed into our halting machine, H. All right, and then we still have the same process where the inputs, if it's yes, then it equals to loop. And if it's no, it's going to equal, not loop, or basically let me write halt instead. All right, and this now encapsulates the machine. So now there's going to be outputs that come from this. And if we loop, we're going to say that it doesn't halt. And if we halt, then we're going to say, yes, we're going to halt. So now the issue becomes is that the input H plus, if we put through here, if we halt, well, then the end result is going to be doesn't halt. Well, then if the starting function is to not halt, well, then the end result becomes to halt. So we now enter into a paradox where the output of the halting machine halts and doesn't halt at the same time, or it doesn't halt and halts at the same time. And in standard modern-day computers, it's kind of impossible to have a yes and a no occurring at the same time. Now, you can make a loose argument to say, well, if you know about quantum computing, there is cases within quantum computing where you can have, due to I'm blanking over here. You can have situations where you can have ones and zeros occur at the same time. And so the problem with that is that quantum computing works off of different physics and different different laws, so to say, based off the quantum laws, where solid-state computers, or the computers that we work with every day, cannot do that because they don't have the ability to be able to do things like that. So, I mean, we're not going to kind of reference quantum computing because that's sort of a different league. But for the standard computing and the algorithms that we use for standard computers, it's not possible to be halting and not halting at the same time. So, anyway, so I just wanted to give a little bit of information based on, the halting problem that Turing came up with. And this is just a very loose description of it. It's more complex and complicated than that. But for the sake of just to kind of give you a little bit better understanding of what halting is referring to, that's basically what Turing was coming up with. All right. So like I was saying earlier about intractable problems. So a problem is considered intractable if there's an algorithm to solve it, but the algorithm is not efficient enough to solve it. So as the number of inputs grow, what happens when they grow so large, we can solve the intractable problems for the small input sizes, but as they grow large, they become a little bit more unmanageable. And as you'll see, the values will grow consistently huge. So for large input sizes, we can use the fact that there are such problems to protect us, for example, protecting our passwords from risks of hacking, or for also if we're going to see we're also going to see for certain intractable problems that we could sometimes use heuristic algorithms. All right, so ultimately, intractable problems fine when we're dealing with small numbers of inputs. A handful of I'm trying to think of a really good example to probably give, because using like a password is not a good example, because, well, if you create a password, I guess using a password as an example, if you create a very small 3-letter password, it's really not going to be that hard to end up solving or getting an answer for that, because there's a limited number of inputs, limited number of possibilities. Therefore, using intractability, you can find that password fairly easy. But when you extend that password out into a longer password using numbers, symbols, capitals, etc., the problem then, the number of input possibilities becomes so great that it becomes that much harder for intractability to find the solution. which is why a lot of passwords now, they will tell you that you have to have certain criteria met before they will accept the password for the account that you create. All cases typically are considered an intractable problem, but an intractable problem is one for which the algorithms to solve it all require exponential amounts of time or space, which will give you a sense of how inefficient that is. So to kind of give you a better understanding of intractability, so let's consider, you can kind of read the story over here. But let's consider the story of a king. So we have a king that has agreed to pay his sage 1 grain of rice on the first square. And then on the second square, all right, that grain of rice is doubled from 1 to 2. The third square, all right, doubling that, so we have 4. And then on the fourth square, we have double that, which is 8, and so on and so far, and so on and so on and so on. So the doubling will occur for each square. And so if the sage could ultimately beat the king in a game of chess, then the sage will win, the amount of grains of rice for every square doubled as we continue on to the final square on the chessboard. So if you carry that out basically to the end, what eventually happens is that the king is going to end up needing to pay the sage about 210 billion tons of rice if he loses. So in this story, the king obviously doesn't really understand the concept of exponential growth. All right, so go down here. So what we see here, these are some graphs kind of showing you the difference between the exponential growth curve, which is what you see at the bottom, this red line here. It starts out fairly shallow with no growth at all. But then very quickly, it grows extremely fast, almost straight shot line up. And when you compare this to what are known as polynomial curves, all right, which are the n squared, n cubed, and n to the 4 over here, you can see that the exponential curve grows at a much faster rate than that of the quadratic curves, or the polynomial curves, and especially the quadratic curve down here, which we know a quadratic curve is to be a parabola. But with regards to the exponential curves, I mean, it's almost, in retrospect, has seemed to flatten out the quadratic curve to make it almost look linear. So as you can see, the exponential curve grows at a much faster rate than the quadratic curve. And this, so remember, this was our characterization for the bubble sort algorithm. So when we talked about bubble sort, we used the n squared method to detect bubble sort. And if you remember with bubble sort, we always did the half of a half of a half in order to find out, the number in question that we needed to target. So in the case where we've got a y-axis with a very large numbers on it, so the quadratic curve looks like I said almost flat compared to the exponential curve. So this could probably be even easier seen if you like looking at like tables and charts. So if we go on to the next slide, and we can kind of compare the items. So what we see, we have functions 2 to the n, the exponential one, compared to n squared and cubed, and to the 4th. So what you can see here for certain problems, even where the number of inputs is as low as 64 elements or 64 bits, 64, 128, 512, all the way down to 4096, all the way down to 1,048,000, etc. So what we see that the next algorithm would take time or space proportional to 1.8 times 10 to the 19th power, which is what we see over here in the exponential 2 to the n power, which is obviously a staggeringly large number for these types of problems. That's completely out of the question, so that, when you would want to use this in order to solve the problem, for as few as 1,000 inputs that we see here using the bubble sort, or 262,000 for the cubic, 16 million for the quartic, and etc. So using an intractable problem, using these types of algorithms, it would totally be not efficient at all by using this method, because the exponential growth within that is just too large. And then as you can see, when you get even further down to the number of inputs here, the exponential growth rate is just massive beyond what you can possibly comprehend. And as we get further down here, there really isn't a number to sort of express what a million inputs would do using exponential growth. All right, so So let's look at an example of using an intractable problem in order to protect us. And what we want to do is we want to look at the problem of password guessing. So there's different ways to attack somebody's password, as you can see over here. You could you could use the dictionary attack. So you can try looking up words in a dictionary and trying them to see if it works. But the problem is that's not going to work if the password isn't a word in the dictionary. Now, when we use the word dictionary, I mean, we're not really referring to using literally the dictionary, but using known terminologies may be familiar to somebody. And so that's why they say when you create a password, you should never, use your social security number, your birth date, your month, for birth or whatever. You should always create some sort of unique password that probably you and only you will know alone, because the first thing that any sort of hacker or somebody would do is to basically use those common items to see if they can try to crack into your account using that. Right, and so that's a good reason not to basically use words that are familiar or that can be looked up as your password, because that will basically guarantee the hacker that the entry would work. So in order to, if again the item that you use as a password is not listed in something that is noticeable, well then we would have to go with the brute force method. And the brute force attack is basically where you try every possible password. And so to see however many guesses would basically take in order to crack a password by brute force method. So thinking of it again, like I mentioned earlier, as an example. Let me go down a couple slides here. There we go. So if we have a single letter used as your password, so in that case, you'd only have to look at it a maximum of 26 possibilities. You'd probably obviously get it sooner than that, but 26 guesses would all that would be needed in order for you to find the password. So how about if you use two letters? Well, then you would basically be using 26 times 26, because you would have 26 guesses for the first letter, 26 guesses for the second letter, which would be equivalent to 26 squared. All right, and so that would give you basically a total of 626 possible options to crack. So it's not many guesses. Maybe 626 guesses is tedious from a human standpoint, but when you feed it into an algorithm in a computer, it would be a different story. It'd solve it probably almost instantly. Oops. So what happened now if you had three-letter password? All right. What if you use both upper and lower cases? So you'd have a total of 52 possibilities. So you'd have 26 for the upper, 26 for the lower, which would give you 52. And then because you're using three letters, it would be 52 times 52 times 52, or a total of 52 cubed in their guesses. And so that would then equal roughly about 140,000 plus of possible scenarios that you can try and guess until you find the actual value. Again, it would take a while for a human to monotonously go through it, but a computer system could guess that almost instantly. So in general, if there are a total of m different letters that you're using as symbols in your password, then for a password of length n, guessing the password would take m to the n guesses. So the way to protect your password from brute force algorithm, brute force attack would basically be utilized to choose a password that involves different types of letters, uppercase, lowercase, numbers, special symbols, etc. And that can then turn out to be fairly long. So the longer the password and the more symbols used, the greater the chance becomes that someone will not be able to crack your passcode. All right, and so that's basically the importance behind it all. So this kind of gets into the next piece where I talked about heuristics and heuristic algorithms and how and or why they are used and chosen. So this time we want to look at intractable problems. And so for that, we truly want to solve, for the problems that we truly want to solve. So we saw earlier that we can use intractability to protect us. So if we use extra long passwords with lots of different symbols in them, we can protect our passwords from not only dictionary attack, but from brute force attack. But what about problems now that we truly want to solve? And so for that, one such problem that comes to mind is the traveling salesman problem. So if you're given a list of cities and their distances between them, can you find the shortest path visiting each city once and returning to the starting point? All right. And so that ultimately brings up, how many possible paths do we need in order to optimize in what we need to find? And so ultimately, these are what are referred to as optimization problems. We want to find the best possible solution for optimizing the solution. And the only way to really solve this is to use the brute force algorithm. So to make a list of every possible path through the cities and then choose, all right, which is basically the shortest path and by how many possible paths are there. So if you have n cities, then there's a total of n number of ways to choose the first city. And then once you have chosen, from there, there's n minus 1 ways to choose the next city. And then from once you chose the next two, then there's n minus 2 ways, and so forth and so on. So if you work that out, you get the factorial problem. All right, so the factorial expression n factorial is n times n minus 1 times n minus 2, and so on, until you get down to 1 or 100 factorial, depending on how many, whatever the value of n is equivalent to. All right, and so if that is the case, then you have basically 9.3 times 10 to the 157, which is just a really massive number. All right, and so this big number, it's just a huge number. And so in fact, that the factorial function, all right, and the factorial is greater than 2 to the n is basically what it boils down to. And so our standard example for an exponential function, however, what we want to do is we want to be able to solve this problem, all right, because there is practical applications, for the traveling salesman problem. When we look at networking or when we look at truck routing or in other specific disciplines. All right, let me see. So fortunately, there are what is known as heuristic algorithms, and we can use those to solve this problem in practical ways. So heuristic is an algorithm that produces a fast, correct solution to the problem, but it can't be guaranteed to be optimal. So you would get an effective, efficient route through the n number of cities, but it would not necessarily be the optimal route. All right, and so we can look at one example of the nearest neighbor heuristic for the traveling salesman problem. So it simply states that, and let me get to it. There we go. So the traveling salesman problem, it basically simply states that at each city, what we're going to do is we're going to start at a specific city, whether it be A, B, C, or D, and then we're going to choose the nearest neighboring city as the next city to visit. So in this example, we have 4 cities, A, B, C, D. If you start at the A up here, and we use the nearest neighbor algorithm, then you would get a total for your trip as 57. All right, so the case of what we're doing is we're going from A to B to D to C and then back to A. And these numbers are basically all the mileage or the money that it will cost you for your trip that we have to add up. So 10 plus 11 plus 10 plus 26. All right, the problem now becomes is that is it pretty good? Yes, but ultimately it's not optimal, because if you don't apply the nearest neighbor, if you look at all the possible paths through the 4 cities, starting at A, then you could come up with a shorter path. So in the case the nearest neighbor heuristic failed, in this case specifically, originally the heuristic neighbor algorithm failed to find the optimal solution. Okay, but it gave us a pretty good idea of what the solution should be, right? And that's the idea with heuristic algorithms. We want a practical solution, not a perfect solution. And as you can see with the shortest path, if we traveled from A down to D, over to C to B to A, all right, we would basically be adding 10, 11, 10, 12, 10, and that would leave us with $4 less spent, which that would be optimal because you're saving the most money from there. So before let me continue, let me just double check my time here. All right, so I'm going to do this really quickly because I got under 4 minutes ago. So just to say really quickly how this is used in a company like UPS will use heuristics in order to find this, and they have an AI system or an algorithm called Orion. All right, and what Orion, like the hunter, or what Orion basically does is if this is the entire truck route of a UPS driver, how do we know that the lines connecting each stop is optimal or not? Well, what Orion will do, it will basically take 5 or 6 local stops, and what it will do, it will draw circles around them, and then what it does, it focuses specifically on the stops over here, and it now kind of goes through and looks at all these stops and says, what is optimal? Is the optimal path here, 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 all right? Or is the optimal path here, 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 or, and so on and so forth. All right, so it's going to continue and go through and find what is the most optimal path. Once it finds the optimal path from start here to finish here, it then looks at the next groupings, all right, and we'll decide, is it more optimal to draw from here to here, or is it more optimal to go from here to here, and so on and so forth? Because if we have, normally there's 70, 80 stops in a normal UPS route, well, that becomes a 70 or 80 factorial problem, which the computer system will be bogged down because of the 10 to the exponent number that you're dealing with here. But if you can break them down into 5, 6, 7 stops and then run heuristics on that, it becomes much more manageable. And then from there, you're then looking at trying to put together the chunks of the routes with the neighboring chunks. And you get almost not a perfect system, but you get a close to optimal system when doing that. And it saves the computer processing time, but also it saves the company massive money in the long run. Using a system like this can easily save 30 minutes to an hour on a driver's, within a day for a driver. Therefore, from a company nationwide perspective, there's an hour per driver that they're paying less for, which means most likely they're also paying less on overtime. It's also an hour less of driving, so it's more money saved in gasoline, more money saved on wear and tear in the car. And UPS estimates that they probably save anywhere in the ballpark of about $50 to $80 million a year countrywide just by using this system and dividing using heuristics and dividing up all their stop routes the way they do, the way their system does. So anyway, so we'll cap it there. So we will talk again more next Tuesday. There's one more unit that we got to go over. I'm not going to have any more unit tests because I know we're about 3 weeks away from our final. And next week I should have at least a study guide put together of how you can start preparing for your final. But again, there's going to be one more, I wouldn't want to call it a full unit, but it's a topic about, reading data from a data file and being able to process that information using App Inventor. Anyway, so I hope everybody has a wonderful weekend. Take care. Stay safe. We'll see you next week.